An Arrhenius acid is defined as a compound which, if you dissolve it in water, will increase the concentration of protons in that solution, whereas an Arrhenius base increases the concentration of hydroxides in the solution. Now, these are actually fairly antiquated descriptions of acids and base. We don't use them very much anymore. Instead, we use the Bronsted-Lowry acid and base descriptions, in which a Bronsted-Lowry acid donates protons, and a Bronsted-Lowry base accepts protons, or H pluses. Why should we call an H plus a proton? Well, a hydrogen has one proton and one electron, but a hydrogen ion, H plus, has lost its one electron, which leaves only a proton. So H plus is known as proton. So you could talk about a typical reaction in which hydrofluoric acid reacts with water. Now, hydrofluoric acid is an acid, hence it is likely to donate a proton, according to the Bronsted-Lowry definition. And so it can send a proton over to this water, which will act as a base. Acids react with bases. So this hydrogen fluoride loses the hydrogen being left as just fluoride, and the water accepts that hydrogen ion, that proton, leaving hydronium. Hydronium. Now, it takes a little while to write out the entire equation for the reaction with water. Sometimes, in order to save time, we don't write that entire equation, but instead we just write the dissociation of the acid and presume that water is involved. For example, HF breaks up into two ions, F minus and H plus. Now, this H plus, this cannot actually exist in water. It's extremely unstable. But we write it anyway. When we write it, we really mean hydronium, H3O plus. So instead of writing water as a reactant and hydronium as a product, we get rid of the water as a reactant, and we just write the proton. Now, this reaction involved an acid reacting with a base, and it produced a base and an acid. You see that this acid, it acted as an acid, it left fluoride, which can act as a base if it reacts in the reverse direction. Being that hydrofluoric acid is a weak base, actually acid, the reaction has some established equilibrium. So this fluoride which we produce could further react back with this hydronium and form hydrofluoric acid and water. So we call this fluoride a base. It can act as a base. It can accept a proton from this hydronium. And so we see that HF, it initially is an acid, and whatever is left over is called the conjugate base. And then water, it originally acted as a base, but what's left over after it accepts that proton is called the conjugate acid. That hydronium can further act as an acid in the reverse direction. Ammonia reacts with water. Now, this may not seem intuitive yet, but you should memorize that ammonia or similar compounds, such as the following. So methylamine, ethylamine, and other amines, they act as bases. If you see nitrogen with a couple hydrogens on it, it's probably going to act as a base unless it's ammonium. So ammonia reacts with water. Ammonia will act as the base and water will act as the acid. Being a base, ammonia will accept a proton and you'll be left with the conjugate acid, whatever is left over after ammonia acts as a base, and that is ammonium. And then water, it originally was an acid, and then whatever's left over after it acts as an acid is the conjugate base, hydroxide. So, you might be asked, what is the conjugate base of HBr? You can see that conjugate bases, they're whatever is left over after a compounded acid has acted as an acid. So if HBr has acted as an acid, it's released an H+. And so it loses not only that hydrogen, but the positive charge as well. You're left with Br minus. Whereas we might have the question, what is the conjugate acid of something? Now, a conjugate acid is whatever is left over after something has acted as a base. So if NO2 minus acts as a base, it accepts a proton. What's left? Well, it has an extra hydrogen and an extra positive charge. So it would be HNO2 with no charge. So conjugate bases have lost hydrogens and positive charge. And conjugate acids have gained hydrogens and positive charge. Now, we saw that HF up here, it acted as a weak base, actually acid. It had a incomplete reaction. It had the establishment of some equilibrium in which we had some amount of reactant end product after the reaction has reached equilibrium. However, there are also strong acids. Now, HF, strangely, is not a strong acid. It is a weak acid, even though there are a variety of different hydrohalic acids which are very similar to it, yet are strong acids. HCl, HBr, HI, all of these hydrohalic acids are strong, but HF is a weak acid. You also should be able to recognize nitric acid, perchloric acid, and sulfuric acid as strong acids. They dissociate in water 100%, completely. So when they react, we use single arrows instead of these double arrows. Weak acids, they use those double arrows because some equilibrium is established. The reaction does not go to completion. Now, strong bases are similar to strong acids. They react 100%. Generally, things with hydroxide. Sodium hydroxide, potassium hydroxide, barium hydroxide. These are all well soluble. These not only dissolve within solution, but when they do, they break up into separate ions. For example, sodium hydroxide breaks up into sodium ion dissolved in water and hydroxide ion dissolved in water. Now, calcium hydroxide and magnesium hydroxide are also strong bases. However, they're not well soluble. Now, on the occasions that they do dissolve, they do break up into the ions, calcium and hydroxide. But most calcium hydroxide and magnesium hydroxide will probably stay at the bottom of the solution as solid. So we can describe a strong acid, such as hydrochloric acid, reacting. Being that it's a strong acid, we have this single arrow. It has 100% reaction. Now, if you have some strong acid in water, that strong acid dissociates completely. So in fact, the strongest acid that can be left over after you put a strong acid in water is hydronium. This is the strongest acid possible while water is present. Now, being that hydrochloric acid reacts 100%, this strong acid reacts 100%, the base left over must be very weak. That base left over is unable to react back in the reverse direction. So, in fact, that is an exceptionally weak base. The stronger the acid, the weaker the conjugate base. Here we can see that we have acetic acid. Now, it has 4 hydrogens, but only one is ionizable, or acidic. And that is the hydrogen which is on this oxygen here. Hydrogens on carbon are not ionizable, and so they will not be released when a compound acts as an acid. But this hydrogen on acetic acid is ionizable, is acidic, it can be released to water, and leave acetate and then hydronium. Being that acetic acid is a weak acid, this reaction is reversible, represented by the double arrows here. And so this base that is produced is only a weak base. It is not exceptionally weak. The reaction is able to go to a significant extent in the reverse direction. This acetate is able to act as a fairly reasonable base. Now you might be asked, in which direction or side will an equilibrium lie? For example, for this reaction here, are we more likely to have phosphoric acid or dihydrogen phosphate left over after phosphoric acid is placed in a solution of nitrite? So are we going to have mostly reactants or products after equilibrium is established? Is K going to be less than 1, or is it going to be greater than 1? You can describe this and answer the question by comparing the acidity of your acids or by comparing the acidity of your bases. Here we have phosphoric acid, which is a fairly strong weak acid. Nitrous acid is a weaker acid than phosphoric acid. Being that phosphoric acid is a stronger acid than nitrous acid, phosphoric acid is more able to give up a proton and form nitrous acid than nitrous acid is able to give up a proton and form phosphoric acid. And so the stronger acid is more likely to react, and so the reaction should shift away from that. Thanks for watching, guys.